Hey, good afternoon, everyone. So we are continuing with chapter 8, which is on rotation of rigid bodies. So what have we learned so far? So I'm going to do a little recap before we continue on with chapter 8. So we have learned about torque is equal to the cross product of R and F. R is the radius and F is your force. And the cross sign here means that the force has to be perpendicular to R. So in other words, torque is equal to RF perpendicular, or you can expand this equation to become RF sine theta. And theta is the angle between the two vectors. Angle between R and F. So that is torque for now. So if we are going to imagine it in terms of like a free body diagram or something like that, so imagine we have a seesaw and this is the axis of rotation. So I can apply weight over here. I can also apply weight over here. Now, when I apply weight on different sides of the axis of rotation, I will get a different type of movement, either anti-clockwise or clockwise. So if I put on weight over here, this would rotate the object this way. And if I put weight over here, it would rotate the object this way. And this is called anti-clockwise. And this is called clockwise because it follows the direction of a clock. In terms of torque, it is going to be either positive or negative. So since torque is R times F perpendicular, this is your R to the F, and clockwise would give you a positive torque. Sorry, negative torque. Clockwise negative. And an anti-clockwise movement, this is your F, this is your R, and the movement it gives is anti-clockwise, therefore you would get a positive torque. If you were to combine all the torques acting on this object, you would get net torque equals to, let's say this is torque number 1 and this is torque number 2, you would get net in the torque is equal to minus torque 1 plus torque number 2, whatever this value is. So this is the net torque acting on this rigid body or on this object. So that is about torque. Now we talked about free body diagrams as well. Okay, we talked about free body diagram of rigid bodies of rigid bodies lah. Okay, so imagine that we have a beam that is connected to, what do you call this, a wall, and this is a hinge, meaning to say it's free to move, rotate upwards or rotate downwards. That is your hinge, and it is also connected to a rope. So in this type of object or our free body diagram, we will have two types of free body diagram. One is net in the F. We're concerned about the net forces acting on this object, and we are also concerned about the torque acting on this object. Now, typically, we only dealt with net forces. But when we have an object that has the tendency to rotate, then we would have this guy over here. As long as it has the tendency to rotate, you know that if you mess up a little bit, it will rotate. Or if the string snaps, it will rotate. Or at any other conditions, it will rotate. So it has that tendency to rotate. Even though it's not rotating, you still need this guy over here. For linear cases where the object can only move translationally, meaning to say you have a box on a ground, you push it, it's not going to rotate, it's just going to move in the x-axis. So this is, you're only concerned about the net F, move in x-axis. But if you have a ball and it has the tendency to rotate and also move forward, so you have to be concerned about both F and torque. Okay, so those are the two things you need to be aware of. One is just moving translationally or in the XYZ. It's not rotating. One has the tendency to rotate because it has a hinge, or sometimes it doesn't have a hinge, but if this string snaps, it would like fall down. And to fall down, it has to rotate. So it has a tendency to rotate. So now, when we're talking about this guy, we would label our forces T, tension, the weight of the beam, and also we would call something over here at the hinge called as R, or the reaction force. Typically, we would resolve the R to become Rx and also Ry. So R is always at your hinge or at your axis of rotation. You have to remember to put it there. Always at the axis of rotation. If you have a ladder that was like, what do you call this, resting on a wall, where is the axis of rotation? Would it be up here or down here? This is A and this is B. Where is the axis of rotation? It has the tendency to rotate. Where would it rotate? Cuba fikir, macam mana dia akan jatuh? At point A or point B? Is the axis of rotation?
B.
Anyone wants to answer A? Okay, if we try to imagine this scenario, the ladder, if it falls, it either goes this way or it falls back down over here. So we can say that, oh, the axis of rotation is here, because either way, it would go here or it would go here, and it would lose contact at this point. It will lose contact. So we know that this will not be our axis of rotation because the axis of rotation is our paksi. Paksi tu tak boleh bergerak. So if it loses contact over here, then that is not our paksi. It's not our axis. So this is our axis. Now try to imagine if this is our axis of rotation. The ladder would move upwards. So that defies logic, right? So janganlah cakap axis of rotation dekat atas ni, because it's not. Okay, so try to imagine everything has some logic to it. So try to visualize how it should be in the real world scenario. Okay, so we have our tension here, our weight. The weight is always at the center of the object or the center of the beam. We have our reaction force. Am I missing anything? We don't have anything else over here. So if I were to write the net torque, I have to find out what is my R for each of these forces. So I shouldn't use this one. I need to find out what is the R for each of these forces. Why is this still a crayon? Silap. Sorry. Green. Okay. So I need to know what is the R with respect to the axis of rotation. What is the R? This is going to be R1. This is going to be R2. And the R for my R, sorry, the radius of my reaction force is going to be 0 because my reaction force is exactly on the axis of rotation. So the radius is equal to 0. So it means that it does not have any torque. So when we're dealing with this type of equation, we need to know what is our R, and oops, this has to be perpendicular. If it's not perpendicular, you need to resolve it to become perpendicular. And then it has to be positive or negative. We don't know, positive, negative. Let's say this is R2 and W. This is our weight. Now we have to define what is our direction, whether it's anti-clockwise or clockwise. So this is our hinge. If I'm applying T this way, this is T perpendicular, it's going to go anti-clockwise. So this guy is going to be a positive. And this guy, this is my axis of rotation. I'm applying weight down here. So it is going to fall clockwise. So this is going to be a negative. Okay, so again, remember to always use your perpendicular forces. If it's not perpendicular, resolve it. Saya tak buat kat sini because we already talked about it in length last class. So that is your free body diagram for net torque. Now the next one is your forces. Net forces. So we have tension, we have weight, we have reaction. We combine this into another free body diagram that everything centered at the center of mass. So we would have T like this. We would have this as our T. I don't know. This is theta maybe. Depends on where your angle is. And then you have your weight. And then you have your reaction force. I can use reaction like this, or I can use the resolved components. I'm going to use that. And then you solve for your forces. So if your net force is equal to 0, that is your condition. Therefore, you know that net in the fx is going to be Rx minus T cosine theta. And your net Fy is going to be Ry minus weight. And this is going to be 0. This is going to be 0. If it's not moving, if it's moving, that's another story. And this is going to be equal to 0. Okay? I forgot one thing. If your object is in equilibrium and it has a tendency to rotate, therefore your condition is net force is equal to 0 and net torque is equal to 0. Kalau if it's moving, then this condition does not apply. Okay? Next. New slide. If you have any questions, please interrupt me. Okay? And then we're going to talk about number 3, the moment of inertia. Chapter 8 has a lot of new stuff. So I have to make sure I'm covering everything. This was torque. This was free body diagram of rigid bodies. If it's in equilibrium, net force is equal to 0. Net torque is equal to 0. Torque, you have that anti-clockwise and clockwise. You have to know whether it's positive or negative from the axis of rotation. And you also have your net forces, and your diagram is different than your rotational diagram. Okay, next one is moment of inertia, or I. Oops. Okay, we also learned about this one. I is equal to mr squared. This is for a single particle that is rotating. So you have a single particle and it is rotating. So this is I equals to mr squared. It's called moment of inertia. So if you have multiple particles rotating, I don't know why we have this situation, but it's sometimes it happens. So we have to find out net mr squared for each particle. So this is going to be m1, m2, m3, m4, and r is from your axis of rotation. Okay, so M1, what is the R? M2, what is the R? If they have the same R, great, you can use the same values. And you have to add them all together to find out what is the moment of inertia for this system. So if this system has 4 particles, you have to add them all together to find out the moment of inertia for this system. Now, sometimes we can't do this. We can't use this equation. Sometimes it gives us complicated objects, such as this ring. So in that case, your moment of inertia becomes integration of R with respect to M. Integration of R squared with respect to M. But we don't want to do that. We just memorize the equation, which is this table. So for thin hoop is mr squared. Okay, just remember this table or just refer to this table when you're doing your web assignment later. Okay, it's a lot, I know. And then number 3 was our moment of inertia. And then from this equation, we also discovered a new equation. So torque is equal to I alpha, right? Sorry, just skip pula. So I is equal to mr squared. This was our basic equation. And torque was Rf. So if we substitute F equals to ma, and I substitute A as what do you call this? R alpha. I would get mr squared alpha, and this becomes I alpha. So this is another equation for torque apart from RF. This is your uh, second equation, sorry. 1, 2, 3, your third equation. Okay, okay, next one. I'm just doing a recap here. We learned everything already. So don't panic. You're not supposed to panic because we already learned this. Okay, what else? Okay, I think we're done with that. No, so now we're going to work and power by torque. So banyak dah kita dah belajar. So ada lagi work and power by torque. So work done by a force in linear motion is given as W equals to F dot ds. Now remember, S is equal to R alpha, right? We learned this in chapter 7, good. And we know that V equals to R omega and A equals to R alpha. So this was the equation that we've learned last time. So if I have a ds over here, I can substitute for r theta, but since this guy has d, this equation also has to have d. What is d? D is your delta. So if I have delta on one side, I need to have delta on the other side, right? So r theta. Since my r doesn't change, I'm saying that my assumption here is that only my theta changed because of rotation. So I need to say that r delta theta, this is ds r d theta. Okay, it's just like simple math here. So you substitute ds for r d theta. So work is equal to f r d theta. And we know that rf, assuming that f is perpendicular, rf is torque. Saya nak tersasul lah. Fr is equal to torque. Torque times d theta is your work done. So this is your equation for work done. D torque d theta. Oh, science word. And then you know that work, the rate of work, dw dt, is power, or work over time is power, right? So if I wanted to say this as dw and this, I want to put in rate, sorry. Tak tahulah kenapa stuttering tiba-tiba. I have work. I want to find out what is the rate of work, or in other words, it's called power. I want to find out what is the rate of work. So I put in my dt here, dw dt. So if I have d over here and I have dt over here, I obviously need to put that into my equation as well. So this becomes torque d theta over dt. D theta over dt is the rate of change of angular displacement, or in other words, it's called omega, angular velocity. So dw dt, which is equal to power, is equal to torque d theta over dt, or omega. Okay, so power is equal to torque omega. So you have two new equations here. Work is equal to torque d theta, or torque change in theta, and P is equal to torque. You just put your time over here to get your power. So this becomes the change in theta over the change in time, or omega. Okay, so my suggestion is to memorize work equation, which is torque change in theta. You know that power is equal to the rate of change in work. So you just add in dt down here, and you know that delta theta over delta t is just omega, so it works out. If you want to memorize it that way, just find out what works for you, okay? Okay, next one, we have two new equations now. We have another new equation, it's called rotational kinetic energy. So K for linear motion, the kinetic energy for linear motion, we know that is 1/2 mv squared, right? This was what we have learned so far and we have used in many, many circumstances. We also have rotational kinetic energy because why not? It's moving, right? So K is equal to 1 over 2m. They substitute V equals to R omega. We know this already. V equals to R omega. This is squared. And expanding this is for a single particle. Now remember, if we have an object such as a ring, we have many, 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 many particles that we need to calculate the moment of inertia. So we don't want to do that. We want to know, hey, what is the moment of inertia for this guy? And we use the table or we use integration, right? So same case here, your kinetic energy for a for a rotating rigid body is actually K equals to 1 over 2 I omega squared. Looks similar to 1 over 2 mv squared. Sama nampak sama. So again, 1 over 2 I is your moment of inertia. Your omega is your angular velocity. They all are like tied together. So again, I want to like try to relate this to you guys. We saw that torque was equal to I alpha. This is also similar to force equals to ma, whereby your I is your mass, your alpha is your A. Now, what other circumstances do we see this relation? Do we have others? And then we had, okay, so far ini je kot. And then the next one, torque is equal to I alpha and force is equal to ma. We have our K equals to 1 over 2 mv squared. And the rotational rigid body for kinetic energy of a rotating rigid body is 1 over 2 I omega squared. So I is m, omega is v. If you don't want to memorize this equation, you can just memorize the linear form and you change it like what I did just now. Okay. Okay, never mind that one. And then, of course, when we have kinetic energy, we also have the work energy theorem. This was the work energy theorem in chapter 4 that we have learned. So W net is equal to 1 over 2 mv squared minus 1 over 2 mu squared. When you have a change in kinetic energy, therefore you would have work done. If you don't have any change in kinetic energy, then you don't have work. This is what we've learned in chapter 4. Same case here. If we have a change in angular displacement, if we have a change in angular velocity, therefore we would have work. Sama juga kat sini ya. So 1 over 2 I omega squared minus 1 over 2 I omega naught squared. Sama macam 1 over 2 mv squared minus 1 over 2 mv naught squared or mu squared. Okay, yay, habis teori sekejap. So we have two examples here. I want everyone to try. I want to give you guys 5 minutes to try example 8.4 and okay, 8.4 dulu lah. Okay, 8.4, I'm going to ask someone to help me. An engine delivers a torque. So torque is given as 280 nanometer at 3,808 RPM. What is this quantity? What is it called? Is it alpha? Is it
omega?
Omega.
So this is angular velocity. So this is your omega is equal to 3,800 RPM. What is the power of the engine? So it's asking you to find out what is power. Now I'm going to give you guys the equation because kita baru belajar. So work is torque change in theta and P is equal to torque omega. Okay, so it's kind of straightforward. What else do I need to know? What else do I need to do to find power here? Can I use it as it is? Come on, guys. Senang je ni.
Yes.
Boleh pakai. Okay, kita cuba. So P is equal to torque omega. So this is 280 Newton per meter. And my omega is 3,800 revolutions per minute. What is this unit for power? What is the unit?
Watt.
What?
Okay, watt. Okay, so watt. How is watt derived? Macam Newton is MA, right? Kilogram times meter per second squared. How is watt derived? It is work
over time.
Yes, work over time. So work over time, what is the unit for work over time?
Joule.
Joules per second. Okay, so joules per second. So torque is 280 Newton per meter. This is 3,800 revolutions per minute. I don't see any joules per second going on here. What do I need to change?
Kena tukar to RPS.
I have to change the RPM to what? What is the SI unit for omega?
Radian per second.
Radians per second. Okay, so everyone is still awake. I just wanted to check. Okay, so let's move it over here. And P is here. So let's change our RPM first. So let's use a different color for that. Pink. So this is revolution per minute. I want to write it in this form. Revolutions per minute. So if I want to get rid of revolution, it would be 2 pi radians over 1 revolution. Now I can cancel out revolution. And then I want to get rid of minutes. 1 minute is equal to 60 seconds. Now I have that second somewhere. So 3,800 times 2 pi divided by 60. Can someone calculate that for me? I don't have my calculator.
397.9.
397.94.
94.
Tak ada. Okay, 397.9 radians per second. So I substitute that. So this is torque. And our omega is now 397.9 radians per second. How do I get joules from Newton and per meter and radian? I have the second, so it's good. How do I get joules? Tak ada orang tegur saya. Newton meter lah. Betul. How do I get joules, guys? Okay, what is the equation for work? What is the equation for work?
Force times displacement.
Force times displacement. Okay, so force times displacement dot S. What is the unit for force and displacement?
Force Newton.
Newton and
Newton meter.
Newton meter.
Displacement.
It is also equal to joules. So this is already joules, 280 joules. And you times it with 397.9 radians per second. So the radian is tricky, yeah? When it's there, you just leave it. I don't know why. Don't ask me. This is like math people when you could do. I don't know why. But when you have radians and it's stuck there and you don't know how to cancel it, just leave it there. Okay. So now it becomes, what's the final answer? 280 times 397.9. Dapat jawapan berapa? Anyone? What's the answer?
11423.2.
11423.
111.2.
111. 111.
423.2.
423.2. Oh, banyaknya. Oh, betul lah sebab 3. 0.2, and the unit is going to be joules per second or watt. Okay, so just like recap of previous chapters. So work is force times displacement, Newton meter or joules, right? So Newton meter is also equal to joules. If you have radian in your equation, you just leave it. As long as it is in SI unit, you're good. Okay, kalau di dalam revolution per minute, you need to change it to radians. Okay, radians ni tiba-tiba dia hilang. I don't know why. And I don't know how to explain it to. Itu kelemahan saya lah. Saya tak tahu nak explain pasal radians ni. Okay, next one. So, so let's see the answer. Betul tak? An engine delivers so 280, 3,800. Change it to, okay, there's no answer here. Never mind. Okay, next one. Duplicate slide. Okay, let's do this one. Can I give everyone like 5 minutes to do this one? How much network is required to accelerate it from rest? So it's telling you omega is initially 0, and then you have another omega final of 1 revolution in 8 minutes. So 1 revolution in 8 seconds, sorry. A merry-go-round, assume a solid disk. Okay, sorry, saya punya merry-go-round saya ingat. Okay, ada paksi kat sini. So dia akan rotate macam ni. So this is your merry-go-round. Has a mass of 1640 kilogram. Mass is 164 kilogram. Radius of 7.5. So this is the radius over here. From the axis of rotation, this is your radius. Meter. This is kilogram. How much net work is required to accelerate it from rest to rotate at the rate of 1 revolution in 8 seconds. So what equation should I use here? I have 2 omegas, I have mass, I have radius. What should I do with this information? It's asking about net work. These are 7.5 meter. Okay, tak apalah, saya kasih hint. Network energy theorem. What is the equation for that?
1/2
1/2
Okay.
I
And-
omega final square.
Work net is equal to 1/2 I omega squared
minus
minus 1/2
1/2
I omega
omega square.
omega squared, omega naught squared, right? So omega
Yes.
ataupun yes, omega initial, betul. So here we have our omega naught, which is 0. So yay over here. But our omega final is in revolution over 8 seconds. So how do we change this one? What do we times it with?
2 pi rad over 1 revolution.
Okay. So 1/2 I. Okay, we still don't know what is our I. So let's see what is our I. Let's refer to our table. So it is a merry-go-round. It's a solid disc, solid cylindrical disc. It kind of looks like this, cuma dia nipis sikit lah. So this is a solid cylinder of radius r. The axis of rotation is through the center. It kind of looks out like our merry-go-round, so we can use 1/2 mr squared. So let's use that. Okay, so abaikan merry-go-round yang saya ingat ni. So your I is, saya tahu lah kenapa hari ni saya menunjukkan comot. So I is equal to 1/2 mr squared. So 1/2, the mass is 1640, and the radius of this merry-go-round from the axis of rotation is 7.5 squared. So this is your I. So your W net is 1/2 I and your omega squared, which is 1 revolution over 8 seconds times 2 pi radians over 1 revolution. So this cancels out. It becomes 2 pi over 8, right? So if I were to write this nicely, I'm going to try my best. Saya tak tahu kenapa hari ni saya punya grip tak betul. So it becomes W net, okay, 1 over 2 I omega squared, which is equal to 1 over 2, 1 over 2, 1640.7.5 squared. Ada 2 1 over 2 kat sini. So kadang-kadang orang tersilap dia tinggalkan satu je 1 over 2. So don't make that mistake. Put it in brackets if it confuses you. And then your omega is simply 2 pi over 8. And this also needs to be squared. So the problem with this equation that I've seen students make is that you miss out on the square, you miss out on the 1 over 2. Do not do that. Please double check your equation. Banyak benda yang redundant, so you easily forget. Okay, macam 2 square ni ada 2 kali, 1 over 2 pun ada 2 kali depending on your eye. So take note of that, okay? So that is the answer. I don't know what it is, but it should give you the right answer. Okay? Dah jawab soalan betul ke? Okay dah. Okay, so this is what we get over here. Looks the same, no answer because saya yang buat jawapan. Sebab tu saya tak tulis jawapan akhir. Alright, next one. Okay, so what have we learned just now? We learned about work, right? Kita recap sekejap before everyone lupa. We talked about work of a rotating rigid body and it is equal to torque change in theta, or we can write it as torque d theta. So this is work. Now power is actually work. Sorry, this is the unit is in joules. Walaupun dia rotating, it's still in joules. So power is the rate of work done, right? Or we can say dW dt. And if I wanted to find out what is my rotating, the power of a rotating object, I can use this equation and try to, you know, make it work. Torque is equal to d theta dt. So my work equation is now dw dt. I added the dt over here. So it becomes power. Okay, so power is equal to torque omega. So the unit is still watts or capital W. Okay, so that is your power or joules per second. Okay, next one. So now we're talking about angular momentum. Just now we talked about work, power, and W net, right? W net is equal to, sorry, kinetic energy, 1 over 2 I omega squared, and then we had the omega net, 1 over 2 I omega squared minus 1 over 2 I omega naught squared. So those are like, we can just like convert the equation from linear to rotational. Quite easy if you ask me. So next one is angular momentum. So momentum in linear form. Momentum in linear. Kita dah belajar P equals to mv. Now, if we want to make it angular, of course, now it is called L. M, mass is I, right? V is omega. That is what you get. L equals to I omega. Of course, there's some derivation going on. We can do that really quickly. Kejap. So L is given as R times P. Sama macam oh tak sama. V is equal to R omega, A equals to R alpha. Yang ni terbalik. Macam torque equals to M, torque equals to M dulu. Torque equals to RF, L equals to RP. So di diorang dua ni macam special case. Remember I told you torque is a special case. It doesn't follow the linear rotational. Because this one is rotational, this is linear. It doesn't follow the V equals to R omega, A equals to R alpha, S equals to R theta. It doesn't follow this convention. it is special, just like angular momentum. So torque is equal to Rf. Angular momentum L is equal to Rp. P is linear momentum. So dua ni special. Okay, special yang menyusahkan kita sikit lah. Okay, so that is what you get. So if you have a particle that is rotating, it is rotating with a certain momentum. Momentum has mass and velocity. So if your particle is rotating, it would have some rotational momentum. And it is rotating with respect to the axis. This is the radius. Macam pendulum lah. Pendulum that is connected to a string. It is rotating in this direction. So the angular momentum is R times mv ataupun the cross product of radius with linear momentum. Okay, so if L is Rp and P is equal to mv and V is equal to R omega, so this guy is R omega, so you would have two R's, one M, and this one is keluar. So mr squared omega. This guy is I. So this is how you get L is equal to I omega. Do you have to derive it? No, just memorize the equation. Okay, and the units is, what is it? Apa angular momentum unit? Do you have it in book? So I is, it could be straightforward. I don't know. I need to double check. So that is chapter 8. What is the unit for angular momentum? Does it say? It doesn't say. I need to check my textbook. Give me a minute. I think you guys are sleepy today. Are you guys? Macam tak berapa engaging. Or just tired. So L is equal to, let's see. Can't find it. Ada orang jumpa tak? So it's kilogram times meter squared per second. MV kilogram. Oh, straightforward je lah. Okay. So there's no special SI unit for angular momentum. It's just what it is. So this guy is meter, right? This guy is in meter. P is MV, so it's kilogram. V is meter per second. So it's just meter squared per second kilogram. Or if you want to arrange it, kilogram meter squared per second. So it's straightforward. So just memorize L is equal to R cross P ataupun RP. P as in linear momentum. Then you would remember the SI unit as well. I don't remember it. I should remember it. Okay, so we have another equation, L equals to Rp, or L is equal to I omega when we're using moment of inertia and angular velocity. When we're trying to find the SI unit, you use L equals to Rp, where P is mv. Okay. Between this one. Okay. So when we're talking about momentum, we are also going to talk about the conservation of angular momentum. Now this is like a special case juga lah. From Newton's second law, torque is given as torque equals to I alpha. Now this would, I believe this would surprise you because Newton's second law that we've learned so far is F equals to ma. But for the rotational, for a rotating rigid body, Newton's second law is torque is equal to I alpha. So that is why you can relate it to F equals to ma, where I is your m and your alpha is your a. So this is based on Newton's second law, even though it doesn't look like it. But angular acceleration is given as alpha equals to d omega ataupun delta omega over dt. Therefore, we can write torque as I d omega dt. What did I do here? Alpha is the rate of change in angular velocity. You put this into your equation, torque becomes I d omega dt. Okay, so when you have torque is equal to I d omega dt, and you know that angular momentum is L I omega, you kind of want to relate these two guys together for whatever reason. Masa tu diorang nak try relatekan lah. Okay, so they tried, said, okay, so we have dWdt here and we have omega here. So how do we make this guy to become dWdt so that we can relate it to torque? So of course, we just use math here. If I have let me try again. So L is equal to I omega. I want it to have dW dt. So if this guy has to have dW dt, this guy has to have dL dt. Okay, so now I have I d omega dt. Oh, it kind of looks like torque. So torque is actually the rate of change in angular momentum, dl dt. So torque is dl dt. L is I omega. Betul tak? Okay, yes. L, saya pun takut silap. L is equal to I omega. Torque is equal to I alpha. But torque and L, ataupun torque and angular momentum, can be related by torque is equal to the rate of change of angular momentum. This guy. Okay, so if torque is 0, meaning to say that you're not applying any force in the rotational sense, there's no external force acting on the rotating object. Kenapa tak ada? Sebab torque is Rf, right? You need to have that F. So if force is not present in a rotating object, there's no external force acting, therefore your angular momentum is conserved. If torque is equal to 0, dl dt is equal to 0, which means that the change in L is equal to 0, which means that L is constant. When L is constant, then only the change in L will be 0. L constant here means L final is equal to L initial. So therefore, if these two guys are the same, the change in L is equal to 0, right? Okay, I'm going to repeat myself here. So torque is I alpha, okay, I alpha. L is I omega. Relating these two guys together, torque is equal to dl dt. Now, if there is no external force exerted on an object that has the tendency to rotate, you know that torque is equal to 0. When your torque is equal to 0, you conserve angular momentum. L is constant. Okay, so why is it important to conserve L? So, principle of conservation of angular momentum. If the net torque on the rigid body is 0, then the total angular momentum on the object will remain constant. L is going to be constant. Okay, so we have an example here. Okay, so a person stands, hands on his side. Okay, dia tengah berdiri. Sorry, hands on his side. Maksudnya dia tengah panggil apa? Senang diri ke? Senang diri kalau kawat. Senang diri kan? Come on guys, help me out here. I don't know kawat. Senang diri ke? Panggil hands on his side. Hands at his side. Okay lah, saya lukis lah. Nasib lah korang Okay. Betul. Oh betul. Saya tak pernah kawat tau by the way. Not proud of it. Tapi saya tak minat. So this guy. Dia tengah letak tangan on his side ataupun tengah senang diri. And he is on a platform that is rotating at a rate. So dah lah dia tengah berdiri. Lepas tu dia duduk atas tempat yang rotating. Macam merry-go-round lah. So this is the platform. Okay, jangan kita abaikan platform ni punya rupa. So platform ni, it is rotating at a rate of 1.3 revolutions per second, RPS. So omega is 1.3 RPS. Okay. If he raises his arm to a horizontal position, macam ni lah. Saya tak tahu ni panggil apa dalam kawat. Tapi that is what he's doing. So again, I'm going to draw my gingerbread man. This is a terrible gingerbread man. Anak saya mesti tak makan kalau saya masak ni. Okay, so this is what happens when he extends his arm, right? And they said that his omega now changes or decreases to 0.8 RPS. Why? By what factor has his moment of inertia changed? Okay, so first question here, I want to ask you guys, is there any torque applied on this guy on this platform? Is there any torque applied? Let's discuss this. Is there any torque? Soalan senang je.
Yes.
Yes? What was it? Yes? Tak tengok. Tadi ada orang jawab tapi saya tak sure siapa. So someone said yes. Where is the torque applied? Oh, macam evil saya punya gingerbread man ni. Betul lah. Okay, ni macam okay sikit. So why is it a yes?
At the platform.
So torque is applied at the platform. Kenapa dia muka evil lah? Saya tak tahu lah. Sekejap. Try sekali. Kalau macam ni, okay better. So you're saying that torque is applied at the platform. Okay, kalau ada orang tolak, yes. Okay, tak apalah. Platform, kita akan abaikan platform tu. Torque ada tak dekat orang ni? Kita abaikan platform tu. Ada tak? So platform ni rotate, yes betul. Bila platform ni rotate, masalah pula kita panggil dia. Orang ni pun akan rotate juga. Betul. You are right when you said that the platform will have some torque if someone was pushing it. But in this question, they didn't mention that. And we're not concerned about the platform. Kita abaikan platform ni. So ideally, there's no torque applied on this man. Okay, kita anggap macam tu lah. Okay, so there is no torque applied on this man. Therefore, torque is equal to 0. Kiranya macam ni anggap platform tu dia tengah gerak because of someone tolak sebelum tu. So it was rotating and tiba-tiba Mamat ni datang. Dia duduk kat situ. I mean dia berdiri kat situ. So he's just using whatever that is left, right? So there's no external torque that is pushing him constantly. Tak ada So there's no F. No F applied. When there is no F applied, torque is also equal to 0 sebab torque is equal to RF. Okay, so this is our assumption here. Assumption kadang-kadang tak betul. So our assumption is torque is 0 here, therefore angular momentum needs to be, if torque is 0, what does L need to be?
Constant.
It has to be constant. So L needs to be constant. So even though he is extending his arm, his L still needs to be constant. Sebab apa? Sebab torque is equal to 0. Walaupun omega berubah, walaupun I berubah, L still needs to be constant. Now L is equal to I omega. Again, it has to be constant. So if my omega was initially, this is our initial omega, 1.3 RPS. Okay, and then our final omega was 0.8 RPS. Dia berubah. What has to change to keep my L constant? What has to change here? Senang je guys. Ada dua je benda kat sini. Omega dah confirm berubah. Adakah I constant atau berubah?
Berubah.
Berubah. So even though you are the same I mean, like, this guy is not changing his mass, right? But when he changes his form, daripada senang diri kepada angkat tangan, his I also changes. Remember, I kita define as when we have one whole object, we wanted to know what was all the R of the particles inside the object. And each particle ada mass masing-masing, and we didn't want to calculate that. What we did was we integrated this whole object to become I. Kita integrate, kita dapat I, equation I. Sama juga kat sini. So when I have this guy over here, I have like the distribution of particles, right? But when this guy extended his arm, that radius of the particles inside his body also changes. Therefore, the I also changes. Now, let's go back to the table that we have learned earlier. Okay, so look at this long uniform rod. We also have a long uniform rod. Both of them have the same length. I'm going to assume they also have the same mass. Kita assume macam tu, eh? So the difference between these two guys is the axis of rotation, which means that the form of where the particles rotate, the particles ada radius yang berbeza. Partikel kat sini radius dia maybe R1. Kat sini partikel dia punya radius is 2R1. So the radius berbeza. Even though they are the same object, but they have different radiuses depending on the axis of rotation. And because of that, I dorang lain. Their eyes are different. Okay, another instance. I have a cylinder and I try to flatten this cylinder. Saya penyek dia play-doh, so that it becomes nipis. Bila dia nipis, radius dia pun mengembang walaupun mass dia tetap sama. It's the same play-doh, I just flattened it. And because of the change in form, the radius is now different. And this radius, let's say it was 5, now my radius is 10. My I, this is my I initial, this is my I number 2. My I1 is not equal to I2 because they have different radiuses. Okay, so if you have a bigger radius, would you have a bigger I or would you have a smaller I? So let's talk about that too. So here, okay, these two objects have the same mass, but one on the left has a greater rotational inertia. This is right, sorry. Saya left and right betul, saya dyslexic. This is your I. It has a greater rotational inertia on the left, and this guy has a smaller rotational inertia, moment of inertia. They have the same mass. They have the same mass. That's the point here. They just change shape. And because of this radius lagi besar daripada radius yang ni, the I pun berbeza. Orang yang ada radius besar, I dia akan lagi besar. Okay, so let's go back to our problem. So I have two guys here, right? No, this is the same guy. Which has this bigger I? Is it A or B? This is A and this is B. Which has a bigger I?
B.
B, right?
B.
If B has a bigger I and L needs to be constant, your omega has to decrease. If this guy, L is constant, this I is smaller, therefore your omega can be bigger to keep the L constant. Okay, so the answer is, apa soalan dia? A person stands hands on his side on a platform that is rotating. If he raises his arm, the speed of rotation decreases to 0.8. Why? Because this guy, this guy had, macam mana cakap ni? we are applying the conservation of angular momentum? The answer is we are applying conservation. Whoops, what happened? Hello, where did it go? Okay, we are applying conservation of L when torque is equal to 0. This is the assumption here that no one is pushing this guy to rotate. Torque is equal to 0. Okay, by what factor has his moment of inertia changed? So they're asking us how much did the I change, by what factor? So we know that L is constant. Satu L yang pertama, L pertama. Satu I naught, satu omega naught. This is the initial one and this is the final one. But they are both equal because L is constant. So I can write them together in one equation. I mean to say equate them together. I final, omega final. So I want to know by what factor did my I change? This is I final, this is I initial. I want to know what is the factor. So I need to know what is IF over I naught. What is the final over the initial? So I'm going to rearrange my equation here. And I need space. Sekejap, Okay, so now that we have equated them together, I want to know what is IF over I naught, which means that I have to bring this guy over here and bring this guy over here. This becomes omega naught over WF ataupun omega final. Omega naught was 1.3. Betul ke ni? Sekejap. I naught, omega naught, IF, omega F. I want IF over omega I naught. So it becomes omega naught over omega F. Okay. 1.3 over 0.8. The units are the same, RPS, and this guy is also RPS. So I don't have to convert. But if I convert, it's fine. Tapi they will cancel out anyway. RPS cancel out with RPS. So 1.3 divided by 0.8. So the answer is 1.625 is the factor that the moment of inertia has changed. Bila dia letak tangan dekat side, dia hanyalah sebiji silinder yang kecil. Bila dia angkat tangan, umpama dia sebiji silinder yang besar. Sebiji, tak tahulah. So, based on the conservation of angular momentum, L needs to be constant because torque is 0. And then they equate I naught omega naught equals to I final omega final to find out what is the change in moment of inertia with respect to the original. Okay, that is the question. So, okay, next one. Oh, have I shown you guys the video of an ice skater yet? Saya rasa macam dah. Pernah tak saya share?
Belum.
Belum saya share.
No.
But if you follow me on
No.
Instagram, I think you have seen it, but never mind. Kita tengok bersama-sama. youtube.com. My God, kenapa ada gambar ni? Sorry. Oh, I'm not sharing, right? Okay, thank God. Am I sharing? Not yet. Okay. Angular momentum. Gambar orang pakai bikini pula. Saya baik tak masuk. Angular momentum ice skater. Okay, so let's watch this one. Let me share screen.
Decades, the Winter Olympic Games has drawn people from across the world to marvel at breathtaking athletics on the snow and ice. One of the most popular events is figure skating. Athletes meld acrobatics, dance, and physics into mesmerizing performances. It is the sheer precision that separates the skilled athlete from the novice. Through years of tireless training, Skaters must learn to understand
Okay,
and use
so this-
angular momentum to become the best in their
So
sport.
this lady, kejap. When she was over here, she was increasing her she was increasing her eye, right? You extend her legs to increase her eye. And she has some velocity. So now when she comes up, she is not extending her legs. She is becoming a smaller cylinder. Let's assume macam tu lah. And her eye drops. When her eye drops, what do you expect to happen? Her speed will increase, right? Kita
In their
tengok lah.
sport.
Tapi tak pula. Sekejap.
Angular momentum
Dia
is the
lagi.
product of a skater's moment of inertia and angular velocity and is represented by the letter L. When the skater is rotating with no net external torque acting on her, angular momentum is conserved. With her arms and leg outward, she increases her moment of inertia, which reduces her angular velocity. As she pulls her arms and leg inward, she is able to spin faster since her angular velocity increases while her moment of inertia decreases. And this is how skaters become champions.
Oh, berkobar. Okay. So that was it. So you saw that when she was extending her arms, her eye was big, so her omega was smaller. But when she closed her arms, her eye became smaller. Therefore, to conserve L, because there's no net external torque, to conserve L, the omega has to increase, and it increased dramatically. Kalau tangan orang tu panjang gila, tu dia kecilkan badan dia, memang jauh beza lah omega tu. Okay, so that is a real world scenario of conservation of angular momentum. And I like that example actually. Did everyone understood that example? Kan saya share short-short sendiri je. Faham tak apa yang berlaku?
Faham.
Faham eh?
Faham betul.
So this is a summary of what we have learned about all the equations in chapter 8. And also a little bit from chapter 7 as well. So we know that S is equal to R theta. Sometimes they call it as X, sometimes they call it as S. They mean the same thing. So S is equal to R theta. S is your linear displacement, okay? And your angular displacement is theta. They are related by R, radius. And then you have your velocity, linear quantity, and your angular velocity. They are related by radius, R. So V equals to R omega. And then you have acceleration, linear acceleration. You also have angular acceleration alpha. A is equal to R alpha. So this one, yang ni sama kumpulan lah, dia sama gang. Yang lain ni dah macam huru hara. So mass, we have mass in linear quantity. In angular quantity, mass is known as the moment of inertia I. And this is equal to I equals to mr squared for a single particle. If you have more particles, you need to add them all together, mr squared. If it is difficult to identify the particles ataupun it's like a whole object with many particles, you use the table ataupun you integrate. So I is that. It is the equivalent of mass in linear quantity. And then you have your momentum in linear quantity, which is P. Your angular quantity of momentum is angular momentum L, and L is related to P by L equals to RP. Tak sama macam S R theta V R omega, because this is angular and this is linear, dia terbalik. Okay, and L is also equal to I omega. That's your another equation. And then you have torque. Torque is equivalent to force in linear quantity. Torque is related to F by torque equals to RF. Yang ni ditulis R perpendicular to P kan? But it can be R P perpendicular, R F perpendicular. Asalkan ada satu komponen, asalkan ada satu kuantiti yang perpendicular. Sebab dia cross product. Okay? Mana-mana pun boleh asalkan perpendicular, salah satu. So this is angular, this is linear, and we also have another equation for torque, which is I alpha. Okay, next one. Whoops, ni apa? And then we also have energy for in rotational dynamics. Kinetic energy in linear is 1/2 mv squared. M is I, V is omega. So this is your angular relation. Then you have work. F equals to force that is parallel to displacement. Parallel, this is parallel sign. Your work is torque, theta. And then for power or torque, change in theta. Sama, And then your power P equals to FV or work over time. This is equal to P torque omega. And I would suggest to just remember work punya equation and find out power from work, because power is rate of work. And then we had F equals to MA. What time do we have more time? Okay, F equals to MA. Net in the F equals to MA. And then we have net in the torque equals to I alpha. Kita tak belajar lagi pakai condition ni, but we will. For equilibrium, net in the F is equal to 0, which is Fx equals to 0. And also net in the Fy equals to 0. And then we have torque equals to 0 in equilibrium. In equilibrium, these two conditions must be satisfied. For an object that has the tendency to rotate, must be satisfied for equilibrium condition. Okay, so this is the condition when we had movement, right? We had, what did I call it? Non-equilibrium, I don't remember. But when your object is not in equilibrium, your condition is net F equals to MA, right? Sama juga, when your object is rotating, you know that it has torque. So therefore, net torque, the condition is I alpha. Okay, so we have work energy theorem linear. It is 1 over 2 mv squared minus 1 over 2 mu squared. Sama juga, just translate it to angular quantity. And then the conservation of momentum when external force is equal to 0, total momentum is constant. This was back in chapter 3, I believe. When external torque is equal to 0, total angular momentum L is constant. This is P. Change in P was equal to 0 when F is equal to 0. Okay, sama kat sini. L is constant, change in L is 0 when torque is equal to 0. This means it is constant. This means it is P is constant. Okay, sama je. It's just like translating it into the rotational world. Okay, let's take a 7-minute break and then we will learn about the final section of this chapter. If you have any questions, you can ask me. If not, take your break. We will come back at 3:38. Okay. Soalan tak? Kalau ada, tanya. Where's my phone? 38. Hello, I'm back. I hope everyone is back too. Okay, let's continue. Also not share screen. Okay. Okay, let's continue with this part, rolling bodies. This is the final part of chapter 8. So rolling bodies is actually the combination of linear motion and also rotational motion. I've mentioned this to you before. When we have a tire, it's moving forward at the same time it's also rotating. Therefore, it has both translational, it's moving forward in the x-axis, it's also rotating with some angular displacement. Okay, so this is actually called rolling bodies. Just now we talked about rigid bodies, which is just rotating part, right? Rigid bodies, the rotation of rigid bodies. When they use the word rolling, it means that it has both rotation and also translation. It's a weird word, I feel, but this is what they call it, rolling bodies. Okay, kenapa tebal sangat ni? Kejap. Okay, so rolling bodies can be considered as the combination of linear and also rotational, just like this tire. And this is another example. You have this tire of a bicycle and it is also rotating and also moving downwards at the same time. It is also called a rolling body. Oh, this row cerita pasal kinetic energy. Kinetic energy pula. Dia punya free body diagram. So the free body diagram for this tire, before it was rotating, it has friction and also mg. Kita assume dia dekat sini. It has mg and also friction that is parallel to the surface. Now, when it starts rotating, whatever force that has some component that is perpendicular to the radius, in this case, friction, that is your torque. Ada torque lah for the friction. For the mg, you need to find out what is the perpendicular component. Tak apa, nanti kita akan buat example later on. This example is not really clear. Okay, so we have a different equation for kinetic energy. Previously, it was linear kinetic energy ataupun rotational kinetic energy. Now, if we have a rolling body, which means that it has both the rotational and also the translation, we need to have two types of kinetic energy. One kinetic energy for the linear part, which is the translation, and one part of the kinetic energy as for the rotating part. So it becomes K equals to 1/2 mv squared plus 1/2 I omega squared. This is specifically for a rolling body. If it is just rotating, then it is just 1/2 I omega squared. If it is just a box that is being moved forward, then it is just 1/2 mv squared. If it has both the rotating and the translation, we need to have both. This is the linear part, the translation, and also this is the rotational part. So when we have kinetic energy, we know that we're going to talk about energy, right? So we also have the conservation of energy for rolling bodies. Now let's say we don't lose any energy due to friction for this tire that is rotating and rolling down this hill. This tire is rolling down this hill, it is rotating and also translating ataupun moving forward. So you know that the E initial will be equal to the E final, and they are not going to be impacted by work done by non-conservative forces. WNC tak ada kat sini. So EI is equal to EF. We have gravitational potential energy and maybe kinetic energy, and down here we can say GPE and also KE. Kenapa saya pakai GPE? Pakai U UG. So there is no spring over here, so there's no US. So these are the only two things that I'm interested in to find out about conservation of energy. So for my equation E initial, I would have UGI plus KEI, and it is equal to UG final plus KE final. Now my UGI is based on the height of this tire is going to be mgh, mass of the tire, g, gravitational force, gravitational acceleration, h is the height of the tire. And since this guy starts at rest, I'm assuming that dia tak cakap pun, tapi saya nak memudahkan hidup saya cakap dia starts at rest. Therefore, we know that our KEI is equal to 0. So when it reaches this end, the H is now equals to 0. This is 0 and this is H. Therefore, your UGF is now equal to 0. But you have some KEF over here. Now, since our tire is also rotating and also moving forward, your KEF is special and it has to have 1 over 2 mv squared, 1 over 2 I omega squared. So kena ada dua-dua ni. So it becomes 1 over 2 mv squared, v linear, and 1 over 2 I moment of inertia, angular displacement, angular velocity squared. Okay, so this is the equation that you have. Yang ni dorang dah arrange macam mana ni? Oh, constant. Yeah, betul lah tu. So this is going to be I, then the final mgh final, 1 over 2 mv final squared plus 1 over 2 I omega final squared. Sorry to sound buruk. But this is the right way of writing it. Okay, this is how we learned it back in chapter 4, I think. Okay, so use that again. If it is rolling, tambah je lah the 1 over 2 I omega squared in your KE. That is it. Itu sahaja yang berbeza kat sini. The rest is the same. Okay, so we have an example here. A bowling ball of mass 7.3. Dah ada solution, tak apa. A bowling ball of mass 7.3 kilogram and radius of 9 centimeter ataupun R is equal to 0.09 meter rolls without slipping down a lane. Now they use the phrase rolls without slipping. It actually means that bila dia gerak ni, dia rotate kan? Dia rotate je. And sambil tu dia gerak ke depan. Kalau dia slipping, if it slips, which means that there is some part in this motion that the rotation stops. We don't want that. It means that it is not going to be uniform. So kalau dia rotating, if it rolls with slipping, I have this ball, it rolls with slipping, I rotate, moving forward, rotate, and then tiba-tiba dia gelincir, licin ke apa ke tak tahu, dia akan gerak macam ni. Sekejap and then dia sambung rotate. Kiranya at this part in time, it does not rotate. It only moves forward. This is called slipping. Now imagine this is you. You're not rotating. I'm telling that you are slipping. Imagine you are walking on the bathroom, you slip. What happens? You move forward, right? You move forward, tergelincir. So this is what happens here. When you roll with slipping, this ball is not rotating, it is slipping, dia tergelincir. Bermaksud kat sini, rotation stops momentarily. And we don't like this because it tells us that this motion is not uniform. Kita nak motion yang uniform, senang hidup kita. So when it rotates and also moves forward, we can easily predict it. But when it slips, there's a slight change to that. So akan ada percentage error kalau kita assume it's uniform, stuff like that. Okay, so that is what it means when an object is rolling without slipping. Dia uniform lah rotation and also the movement forward tu. Down a lane at 3.3 meter per second, this is your V. 3.3 meter per second. Calculate its total kinetic energy. So it's rolling, therefore you know that you will have 1 over 2 mv squared plus 1 over 2 I omega squared. For a bowling ball, the I is given as 2 over 5 mr squared. So you just put that into your equation. And the omega, dia tukarkan jadi linear. So V equals to R omega, right? So you want this omega, so it change, omega becomes V over R. So this is what you get, V over R squared. So now everything is in linear quantity M is linear quantity, V is linear quantity, R is linear quantity, V is linear quantity. So you can easily use whatever info that you have over here. So now it becomes 1/2 mv squared. They expanded this equation and it becomes 1/5 mv squared. It becomes 7/10 mv squared. Just plug in the equation. So it's quite easy. You just have to identify whether an object is moving translationally or if it is rolling without slipping. Okay. Next one. A ball of mass 0.5 kilogram and a radius of 0.03 meter rolls without slipping, meaning to say it's uniform, down an inclined plane 30 degrees above the horizontal. So this is your ball. It is rotating and also moving forward. Okay, and at the same time, it is also rotating. If the length of the plane is 0.8 meter and the ball starts from rest, omega naught is equal to, dia tak kasih saya ajar ni. Let's make this our last example. We have another example tapi dia susah sikit, so I want to take some time on this one. Okay, so it means that we have another class on this. Never mind. So this is 0.8, 0.8, and the ball starts from rest. Omega naught is equal to 0. What is its speed when it reaches the end of the plane? What is omega over here? What equation should we use here? Semua dah macam tak larat dah. What equation should we use here? Rolls without slipping. We have apa lagi? Starts from rest. We want to know what is omega final. It rolls without slipping. What should I do here? What is the speed? Let's see. Oh, dia pakai conservation of energy. Okay, so that is easy. Tapi saya malas lah nak buat. Okay, let's continue last class because I'm also tired. Let's continue at this example 8.8. And kita akan sambung free body diagram of linear and rotational yang bergerak. So yang tu susah sikit. So I want to take some time on this. Apa lagi yang penting kat sini? This is the bucket starts from rest and falls. Okay. Okay, so let's continue next class. Do you guys have any questions? I know it was a little bit dry today. So kita belajar je. I hope the ice skater was entertaining, but other than that, memang chapter ni quite dry. If not, if you don't have any questions, have a great rest of the day. I will see you on Thursday. Okay, bye guys.
Thank you, Doctor.
Thank you, Doctor.
Thank you, Doctor. Thank you, Doctor.
Welcome. Bye bye.
Thank you, Doctor. Bye.
Bye bye.
Oh, doktor.
Yes, nak tanya ke?
Thursday ni dia dapat balik ke? Bila dia dapat balik? Rabu ke Thursday?
Alah, Thursday. Betul, kita ada kelas. Betul-betul. Thanks, Ikrim.
See you next week.
Okay, see you next week. Bye-bye.